Okay, Stoyan, are you ready?
Yes, I am.
Okay, welcome everyone back to another week of the experimental math seminar. This week we have Stoyan Dimitrov here to speak to us about moments of permutation statistics and central limit theorems. So please take it away.
Okay, so hi everyone. First, and thanks for this opportunity to speak. It's my favorite seminar, actually. This is the case because the seminar is always very diverse topics and they're always interesting. So hopefully this talk won't be an exclusion. So in this talk, at some point I will mention some connection with the talk of Dr. Z from 2 weeks, 1 week ago actually. So yeah, stay with me. First, let's begin with something simple. So let's consider the set of all set partitions of size n, basically all the partitions of 1 to up to n. And as we know, their count is given by the Bell numbers. So for instance, for n equals 3, we have 5 such set partitions given here. And let's look at the simple statistic over this set. Namely, let's count the number of blocks of size 1 in each set partition. So, for instance, for those set partitions given here, we have 3 singleton blocks, then 1 singleton block, 1, 1, and 0, right? This is the value of x1. Okay, so what we ask is, can we find the summation of this x1 over all set partitions? In other words, we want to know the total number of blocks of size 1 in all set partitions of size n. And this question is important because we can, if we have this sum, we can simply find the expectation of this variable x1 by just dividing by the total number of set partitions, right? And probably all of you can immediately see that the answer is n times bn minus 1, just because if we count all the singleton blocks, in the singleton block, we can put 1 out of n elements, right? And then the rest of the set partition can be formed in bn minus 1 ways, right? So in total, we have n times bn minus 1. And yeah, this was easy, but let's look at a bit more complicated statistic. So let's look at the number of 2 crossings in a set partition. So these are 4 numbers in increasing order, I1, I2, J1, J2. And what we want to have for them is that I1 and J1 and I2 and J2 are in 2 different blocks. This is the definition. And here is a simple example. So for this set partition, we have two crossings, namely 1, 2, 3, 4 and 1, 2, 3, 5. Right? Yeah, they're basically like crossing if we draw the diagram. Okay, so again, the same question. Can we find the aggregate, or in other words, the summation of this statistic over all set partitions? Here, it won't be that easy to find the answer. It was found in 2013, and this is the formula. And you can already see some pattern. Basically, we have some shifted Bell numbers and some stuff in front. But let's look at the higher moments for these 2 statistics. So Chern, Diaconis, Kane and Rhoades developed an approach which allowed them basically to find these formulas for the second moments of these 2 statistics. And as you can see, now the pattern is more clear. So we have some shifted Bell numbers, and in front of them we have some polynomials in N. So this is very interesting, and what they proved in addition was that such formulas can be given for the moments of any statistics over set partitions of a certain family. So if my statistic is in certain large class of statistics, then I have such a formula. And this family of set partition statistics, roughly speaking, is this family of those statistics that can be written as linear combinations of patterns in set partitions. So I will not define patterns in set partitions, but the intuition is this one. Okay, and then the same approach was developed for perfect matchings, which are just subset of the set partitions. And yeah, a similar result holds in this case. So for a family of statistics and perfect matchings, we have that their moments can be written as linear combinations of double factorials, this time with constant coefficients. So here is an example for the same two-crossing statistic. We have that the aggregate, the summation of the second moment over all matchings this time, is given by this formula. And here, these t's are the double factorials. So basically, these are the total number of perfect matchings of a given size. So that's why this is an analog of the previous formulas, because here we have the total number of matchings, perfect matchings of a certain size. And before we had Bell numbers. So these were the total number of set partitions, right? So this is an analog. And yeah, the coefficients can be made to be constant. So the reason is that, okay, here we don't have constant coefficients, but this can be written in another way, basically as some constants time t 2n plus I for I in certain range. Right, so yeah, now we will have constant coefficients. All right, so our goal in this talk will be to develop the same approach, but for permutations, and to find whether this is at all possible and what are the implications. Okay, so to do that, we need to define patterns in permutations first. So when we say a permutation, we just mean an ordering of the numbers 1 to n, and by Sn I will denote the set of permutations of size n. Typically, the one-line notation will be used. And also, I will use this notation of arc set for a given permutation, which is just those pairs of numbers such that if we denote them by uv, u is before v in the permutation. Here is a simple example. So basically, every time if I have a permutation pi of size n, the number of elements in the arc set will be just n choose 2. And you'll see why I need this in a minute. And also I will need the definition, the standard definition of a reduction of a sequence of numbers. So the reduction of the sequence of numbers S1 up to Sk will be a permutation of size k. That is basically order isomorphic to the sequence. So here is one example. So 6253 is order isomorphic to 4132, just because the smallest element is 2, and it's at the place of the element 1. The second smallest is 3. It's at the position of the element 2 in the permutation, and so on. Okay, so now I'm ready to define patterns in permutations. So I will use the standard definition for a bivincular pattern. So this is just the triple where in this triple I have a permutation of size k and 2 other sets, which basically they set some other requirements for the positions of the elements and for the values in an occurrence of the pattern. And indeed, this definition of permutation pattern doesn't make sense if we don't talk about occurrence of the pattern. So an occurrence, the formal definition of an occurrence is given here. And usually in the literature, when we say an occurrence of a permutation pattern, we mean basically a subsequence that is order isomorphic to the pattern, right? But here I use a little bit different definition just to be consistent with the previous work. But basically these first two parts of the definition, I can show that this is equivalent to having T1, T2 up to Tk forming a subsequence that is order isomorphic to P, actually. And yes, CFP and DFP, if I have I in CFP, then this indicates that in every occurrence, the ith letter and the I plus first letter will be consecutive in position. Then for DFP, we have requirements for consecutive values. But I will just give some examples here to clarify this. So this is the most basic example. If we just take CFP and DFP to be empty, then we have the so-called classical patterns. And I will just skip the empty CFP and DFP, and I will just write this as the pattern P, the permutation P to denote this classical pattern. And here is an example of an occurrence of this pattern. So 3, 4, 5 is an occurrence of the pattern in this permutation, just because these three elements, the subsequence they form is 3, 5, 4, and this is order isomorphic to 1, 3, 2. Another example, this time for vincular pattern, is when DFP is empty but CFP is not. So this is an example, and in this case 2, 3, 5, 7 is an occurrence of this pattern, this permutation, just because in addition we have 1 belonging to CFP, which indicates that the positions of the numbers corresponding to the 3 and the 2 must be consecutive in the permutation, and this is indeed the case here, just because 5 and 3 are at consecutive positions. Okay, and then finally, when both CFP and DFP are non-empty, we also have requirements for the values. And in this case, we will denote bivincular pattern in this way using the two-line notation. So at the bottom, we will have the usual vincular pattern. At the top, we will have the identity, and for each number in DFP, we will put such a line indicating that in this case, T3 and T4 have consecutive values. And here is an example of an occurrence for this pattern. And indeed, you can check that 5 and 6 obviously have consecutive values in this occurrence. Okay, so now we are ready to define our family of statistics over permutations for which our results would work. So a simple statistic here will be called just a pattern P of size K and some product of two polynomials Q. And basically, we will say that if a statistic can be written in this form, if it's just summation of this polynomial Q over all occurrences of this pattern P, then if there is such a form for my statistic, then I will just say, okay, this is a simple statistic. And yeah, I defined the degree of my statistic just because I will need this later for my theorems. And a general statistic will be just a finite linear combination of simple statistics. So we will see that a lot of popular statistics in the literature fit into this framework. So, for example, if I just look at the number of occurrences of certain pattern, then I would just have Q equals 1. And I will denote this statistic by CMT of P, CMT P of sigma. So here for the pattern P, I can take whatever bivincular pattern I want. So for example, if I take 2, 1, I will look at basically at the number of inversions in sigma, right? If I take, I can take other patterns, for example, this one that is interesting for the community for other reasons, and some other important vincular and bivincular patterns. Another example is this statistic called the descent drop statistic, and it's defined here. And what is interesting here is that it was proved by Carl Peterson and Bridget Tenner that this statistic is equidistributed with another statistic called depth. So it has a similar definition. This is sigma I minus I. So these two are have the same distribution, and in turn, this one is 1/2 of the Spearman-Fuldt rule that was discussed last week by our host, Dr. Z. So Spearman-Fuldt rule, it has pretty much the same definition, but we take the absolute value. And what does this mean is that with our approach, we will be able to find higher moments for this statistic drops. And this would basically be equivalent to finding moments for the Spearman-Fuldt rule. And if you have been here last week, Dr. Z showed us some way to find the higher moments for this statistic using some dynamic programming. Our approach that we show is just an alternative. It would be slower, but much more general. Okay, and finally, let me give an example of a general statistic. It's, for example, if I take all the peaks in a permutation, and if I want to find, let's say, the sum of their squares or their cubes, I can do that. And for example, for the squares, I have that it's a sum of these two simple statistics. So I can, I'll be able to find formulas for the moments. And here is our first result. So basically, this theorem is saying that for any simple statistic, for the aggregates, or in other words, for the first moment, I have this form. So for some coefficient C, this aggregate can be written in this form. And this gives us a way to find a closed form expression, basically to find these coefficients C, right? And that way I will have a closed form for the expectation as well. And how can I find this? Well, I have that many coefficients C that I need to find. And to do that, I will just compute by brute force the left-hand side for n equals k, k plus 1, and k plus this number minus 1. So in this way, I will have a system of linear equations with that many equations and that many unknown variables. So I can just solve it and find the C's. And here are two formulas that are the results of applying this approach. So for example, if I take the number of occurrences of 1, 3, 2, 4, I can get this formula. And one can actually see easily that just by linearity of expectation, this is an equivalent formula. And yeah, I can convert this to this factorial form by using some converting these falling factorials to raising factorials, basically. So this is not a big challenge for classical patterns, but certainly for some other statistics like the descent drops, the linearity of expectation could not work in that immediate way. So here is another formula that we got using the approach I described. And also for a statistic, for a general statistic, we have a similar formula. So the first moment can be written in this form. And here is a formula I got for my example for general statistic. So yeah, the aggregate for the peak square sum is given by this expression. Okay, so now let's make the things more interesting. So can we also show that the higher moments of any statistic is also a statistic? If we do that, we will be able to find similar closed form expressions also for the higher moments, right? Until now, we showed how to do this for the first moment. And okay, so let's do that. I will just say that this is possible. And a key observation here is the following. So if I have a union of two or more occurrences of a given pattern, and then if I take their union, this corresponds to occurrence of another pattern. And why is this important here? Well, if I want to compute higher moments, then I'm basically interested to count how many pairs, triples of occurrences of certain pattern I have with possible repetitions, right? So this is in order to find second, third, and higher moments. And let me give a quick example. So if pi is this permutation, sigma is this pattern, and then if I take these two occurrences of this pattern sigma, then their union here will be just 1, 2, 3, 4, 6, right? And these elements are right here in the permutation. So I can see that this subsequence is an occurrence of another pattern. And this is it. So in fact, what I want to show is that for any pair of occurrences, I have another occurrence of another pattern that is uniquely defined. But let me formalize this. So if I have three patterns, P1, P2, and P3 of these sizes, K1, K2, K3, then a merge of P1 and P2 onto P3 will be just a pair of increasing sequences, functions, M1 and M2, which encode basically such a merge that I showed. So I will denote a merge in this way. And here is a quick example corresponding to what I showed in the previous slide. So these two functions, M1 and M2, basically encode my merge, just because here P1 and P2 are the same pattern. They are 1, 3, 2. And this is my P3. And if you follow M1, you will see that the elements 1, 2, 3 correspond to the elements 1, 4, 5 in this pattern. And you see that yeah, if I take them as a subsequence, they form the same pattern as this one. So yeah, this might be a little confusing, but yeah, it will become more clear. So basically the lemma I'm substantially using here is that what I just said, that for any pair of occurrences of two given patterns, I have another occurrence for another pattern that is corresponding to a merge of the first two patterns. Okay, and by using this lemma, I'm showing that the product of two simple statistics is always a statistic. This is the calculation to do this. And this is very important because by showing this, basically, this allows me to get higher moments, first of simple statistics and then of general statistics. Why is that? Just because I can take f times f to find the second moment, for example, and so forth. And the key here is that if I multiply two simple statistics, I basically can, instead of this double sum, I can, using this lemma, I can sum up just by the occurrences of this merge pattern, P3. And yeah, the result is that this product is actually summation of some other simple statistics. So by definition, this is statistic. Okay, so using this lemma and calculation on the previous slide, I can prove this main result, which is that basically the higher moments of any given statistic can be written in this form as shifted factorials, basically a linear combination of such shifted factorials and constant coefficients. And actually, here is the time to mention that our host, Dr. Z, in a paper from 2004, showed something that is a special case of this corollary of our main result. So this corollary concerns just the case when we look at the number of occurrences of vincular patterns. And in this case, the arc moment has this simple form. And Dr. Z in this great paper found actually a similar thing, but just for the classical patterns. He found that the resulting moment is polynomial in n of this degree r times k. And this is indeed a slight generalization. Okay, and here are some examples. How can we use this corollary and this main theorem? And again, the same approach I described to find these formulas for the higher moments. In this case, I'm taking just the second moments, just because for third and third moments and above, I need more computational power. But yes, these formulas are quite interesting, and you cannot find them easily in another way for such big class of statistics. Okay, and here's another very important corollary that I will use substantially. So again, here we consider just all the statistics that are the number of occurrences of certain pattern. It could be any bivincular pattern, and R could be any higher moment. And basically, this corollary is saying that to find formulas for the higher moments of such statistics, it suffices just to find these numbers, W to the K, to the C, to the D, which are just the number of ways to merge R copies of our pattern P and get a pattern of size K with these constraints for the cardinalities of the C and the D set. And yeah, we will see how can we apply this in a minute. So first, let me apply this corollary to this simple vincular pattern, which is just yeah, the descent pattern. We have 2, 1, and the positions of the numbers corresponding to the 2 and the 1 must be consecutive. So this is the well-known descent statistic. And by using this corollary, we gave this explicit formula for the arc moment, which is quite interesting for me because I couldn't find this in the literature. And basically, the way we proved it is, again, by relying to this corollary. And yeah, we just found these numbers with some inclusion-exclusion arguments. Yeah, so we just considered the possible merges of R copies for this simple pattern. And another similar result is this formula for the higher moments. It's an explicit formula for the arc moment of this bivincular pattern, which, yeah, another name for this statistic is minimal descents. This is how it's known in the literature. Another name is the number of adjacencies. So yeah, this is like the usual descents, but also we want the numbers corresponding to 1 and 2 to be consecutive in value as well. And yeah, we got this formula and we will use it a little bit later to show some limiting result. Okay, so now I will move on to discussing some asymptotic results that we got using our previous results mentioned so far, to in particular to investigate the limiting distribution of, again, this statistic CNT for some pattern P. And it turned out that this statistic, this number of occurrences for this pattern has normal distribution in several cases, and this was first established by Miklos-Bona for arbitrary classical pattern, and then by Lisa Hofer in her master's thesis for arbitrary vincular pattern. However, it turned out that for arbitrary bivincular pattern, this is not true. So we have bivincular patterns for which the limiting distribution is not normal. And we will basically, using this described approach, we will reprove the first and the third fact in a more direct way, and also we will give a lemma that will imply the second fact. Okay. So the way Miklos-Bona proved this central limit theorem for classical patterns is by the method of dependency graphs, basically. So I will not talk about this method, but basically what he showed is that in order to prove this limit theorem, it suffices just to show such a lower bound for the variance of my statistic CNT sigma. And yeah, the way Miklos-Bona proved this bound is by some probabilistic arguments, which are a bit complicated. But here we propose an alternative proof by using our corollary 2 again. So we just write the usual formula for the variance. And since the expectation for this number is already known, we just need to evaluate the second moment here. And we write this quantity just using our corollary. And here, these numbers A sigma of R are just the number of ways to merge 2 copies of sigma and get the pattern of size R. And basically, these are the same like the numbers W, the corollary, but just for yeah, 2 copies of sigma. Okay, so after we simplify, we basically find that in order to establish our theorem, we need to prove this inequality. And after several months of struggling here to prove this. We finally found that it has been done. So this is a lemma in a paper of Burstein and Hasto. And their proof is algebraic. Actually, a very interesting algebraic proof. And I'm personally interested to see a combinatorial proof for this fact. We couldn't find a combinatorial proof, but what we were able to show, to give actually is an interpretation of the right-hand side and to the whole lemma, actually. So I would describe this interpretation here. So yeah, let's look at this set A sigma sigma prime to k minus 1. So if this is the set of triples pi x y, such that pi is of this size and x and y are two subsequences of pi, which are order isomorphic to sigma and sigma prime respectively. And then basically the number I'm interested in, this A sigma to k minus 1, is the number of triples, the cardinality of this set, basically. And yeah, here I give a quick example. So yeah, basically this is the set of merges for these two patterns, 312 and 312. In this case, they're the same, but we want the resulting pattern to be of size 5. And okay, so yeah, this is indeed such a merge, and we want to count how many of these we have for given k and pattern sigma of size k. And basically, we were able to show that this lemma 2 is equivalent to this statement. So so A sigma to k minus 1. So this number of merges is always greater than the expected number of merges A sigma sigma prime, where sigma is fixed and sigma prime is chosen uniformly at random. So this is indeed interesting. Basically, what we did is that we showed that this expectation is 2k minus 1 choose k squared, right? Yeah, actually another the other way around. We showed that this binomial coefficient squared is actually given by the expectation of this quantity. And yeah, we hope that this new interpretation will help us to find a new proof, combinatorial proof of the lemma, but yeah, still we cannot do that. And okay, we run our machinery for the vincular case, the case of arbitrary vincular pattern as well. So if sigma is an arbitrary vincular pattern, then Lisa Hofer, again using some other tools, showed that it suffices to establish such a lower bound for the variance. And here J is the number of blocks of the pattern sigma. So a block here is if we basically the number of segments that must be at consecutive positions. So if I have 4, 3, 1, 2, for example, vincular pattern of this kind, then this just has 2 blocks. Okay. And yeah, we basically got a similar lemma like the one for classical patterns here for vincular patterns. And to do that, this new lemma involves this quantity B sigma mj prime, which is similar to the A's from the classical case. But here we also look at the number of blocks of the resulting pattern. So basically what we want is when we merge 2 patterns with J blocks to get some a pattern with 2j minus 1 walks. And yeah, here is one example. So this permutation has 2 walks, and the resulting pattern after the merge, basically this one, has 3 walks. And yeah, what we showed is that our theorem 10, which implies the central limit theorem for any vincular pattern, the number of occurrences of any vincular pattern, is actually equivalent to proving this inequality here. And this inequality m sigma corresponds to the maximal size of a walk of sigma. And we can easily see that if sigma is a classical pattern, then this maximal size is just 1. And after some simplification, we will get the previous lemma in the classical case of Burstein and Hasto. And also, this is easy to prove if sigma has just 1 walk. Then the maximal size of a walk is k, and yeah, the calculation is very easy. Then you can show that this is indeed true. But however, for arbitrary vincular pattern, we were not able to prove this inequality, but still we would be very interested to see either algebraic or a combinatorial proof here. And finally, for the case of bivincular patterns, we will reprove this well-known result that basically the limiting distribution is not always normal. In particular, it's known that for the minimal descents that we already considered, the number of their occurrences converges to a variable that has Poisson distribution with mean 1. So this has been proved by the statistics community in the past, a long time ago, and yeah, recently, not recently, but like 15 years back, by C.V. Cortel and other people. And basically here we reprove this result as well by using our formula from theorem 7. Yeah, you remember this. This is just the explicit formula for this expectation. And we basically show that the limit of this this expression is the Arc-Bell number. So this allows us to conclude that by the method of moments, the limiting distribution is Poisson with mean 1, just because we know that the arc moment of this Poisson distribution is exactly the Bell number, the Arc-Bell number. Okay, and yeah, obviously we do not always have a normal distribution in this case, in the case of bivincular patterns. So this is one further question that is worth investigating. Can we classify all these bivincular patterns in terms of their limiting distribution for the number of occurrences? And yeah, this question was raised by Lisa Hofer actually. And I will at the end list 2 other questions. So of course, what we desire most is a combinatorial proof of our lemma 2, which I will show again. Yeah, basically, if we find a combinatorial proof of this, we'll be happy, and this would provide some sort of intuitive explanation why this central limit theorem for any classical pattern holds. And okay, this was the first question. Also, for the lemma, for the inequality we gave for the vincular patterns, we also want to find a proof there. And okay, finally, we ask, can we adapt the same interesting approach to other combinatorial structures like trees, polyominoes, and others? And yeah, here I have a small surprise for the end, some quote, particular quote from the abstract, the paper of Dr. Z in 2004 that is on the same subject. I mentioned it already. So you might have forgotten, but probably he had the same ideas back then. And yeah, in the abstract, he mentions that hopefully this paper will be followed by sequels applied to other combinatorial objects like graphical rings, Boolean functions, and random walks. So yeah, perhaps he might say more about these ideas. And in fact, yeah, what he did in this paper is, again, looking at this set of possible merges for some patterns. And yeah, so this idea is not really new, to investigate this set and to try to count the number of merges there. Yes, we might say that he was the first one to see this. Okay, so that was it. Yeah, thanks for the attention. And yeah, I know it was a little bit yeah, too much at some moments, but yeah.
Oh, well, thank you, Stoyan. Everyone, please thank the speaker. Are there any questions for Stoyan? Stoyan, I have one question actually. In the proof in the last thing that you said, this corollary, or where you have this limiting distribution that goes to a Poisson distribution with mean 1. I'm a little rusty in my method of moments. Is it enough to show that just the moments actually converge to a Poisson, to the Bell numbers, or do you actually need to do some more technical argument?
This is a very good question. Actually, I was also wondering about that, and I found some theorems that show some conditions that should be satisfied in order to apply this technique. So basically, there is a theorem that is saying that this suffices, it's enough to show the convergence of moments, especially for the Poisson distribution. And the theorem gives such conditions for arbitrary distribution. So there are some distributions for which cannot do that, but yeah, here we can.
Okay, thank you. Any other questions for the speaker? No? Okay, well, let's thank Stoyan again for the excellent talk. Okay, good to see everyone. We'll see you back here next week with another excellent speaker.